So last class we were still discussing about the nonlinear stability theory, especially for Lyapunov stability for autonomous systems. We were looking at this idea of different concepts with regard to an equilibrium point. We're trying to understand when is an equilibrium point stable, when is it unstable, when is it attractive, and then when it is globally asymptotically stable, locally asymptotically stable, region of attraction, globally exponentially stable, locally exponentially stable. These are some of the concepts we looked at last time. And we looked at with regard to two particular examples. One is with a linear system, where with a spring mass damper system. And then the other one was with a nonlinear stiffness, where we had the stiffness as x minus x cube kind of thing. Right? And we try to understand that there is an I-shaped region inside which the system is stable. Outside of those initial conditions, the system is unstable. Right? So we were kind of trying to understand what these points are. The idea now here is we want to kind of go forward and get a formal definition or formal proof of how can we prove that a system is stable. Okay. So rather than having these concepts of mathematical stability, we have defined what those terms are. We have defined what is stability. But how do I show that a system, a given which is to me, is actually stable or not? What is the method to go about proving stability? Okay? That is what we are going to discuss. And those are the tools which will be most useful for us when we are looking at guidance systems and control systems. Because at the end of the day, suppose you have designed an excellent controller, okay, but the person who is taking up your control logic and implementing it on their vehicle, they want some guarantees. They want to make sure that there is a guarantee that, yes, my controller will be proven to be mathematically stable. And how do I do that? So these are the tools today which we will learn, will be useful in demonstrating those concepts. Okay? And main idea here will be the fact what is called as the Lyapunov function. Okay, and I know that I have put a line here regarding the non-autonomous systems. I'll come to this non-autonomous systems a little later after we have looked at the autonomous systems in detail for once. So we'll come back to this idea. Okay, so the main result which we'll look at is called the Lyapunov's direct method. Okay, so assume that I have a system x dot is equal to f of x with the initial condition x of 0 is equal to x naught. So I'm looking at an initial condition, initial value problem. And it's a autonomous system, which means f doesn't have an explicit dependence on time. I want to now understand that if it has an equilibrium point at x equal to 0, then how do I prove that this equilibrium point is stable or unstable? What is the conditions? So in order to do that, first I define a function v. Okay, a v is a function which maps an n cross 1 vector to positive real part. Okay, so the input is a vector valued state which it takes. The output is a scalar value, and that scalar value is actually positive. So this function is non-negative. Okay. So, and assume that we have defined this function v as a continuously differentiable function, and we also assume that certain properties are satisfied. So if v of x is greater than 0, which means that it is positive definite, and v of 0 is 0. So at the equilibrium point, the value of v is 0, but anywhere other than at the equilibrium point, the value of v is positive. Okay, so we construct a function v such that this first criteria is satisfied. Then we look at v dot, which is the differentiation of v with respect to time, is equal to, is actually less than equal to 0. Okay, so you might be wondering how I got this. This is nothing but the chain rule of differentiation. So v dot of x is nothing but del v by del x times dx by dt. Okay, and dx by dt is nothing but x dot that is equal to f of x. So therefore I can replace this with f of x. Then you get this expression. Okay. So I want that v dot, the derivative, the time derivative of v with respect to the time derivative of v to be less than equal to 0. Now, as v tends to infinity, we want to formulate this function such that as x tends to infinity, v must tend to infinity, which means that the function should be radially unbounded. Okay. If we can find such a function which is satisfying these three properties, okay, so we are defining this function. The user has the choice, so which means you have the choice of finding whatever we want to choose. But as long as it satisfies these three conditions, then the XE equilibrium point is globally stable if W of X is greater than 0. So if this thing is greater than 0, which means this is definitely negative, right? Is that making sense? If W of X is greater than 0, then V dot is definitely negative. If W of X is greater than equal to 0, then V dot must be less than equal to 0. Okay. So in either cases, the XE is globally stable. Okay. Whenever this W of X is positive, semi-definite. Semi-definite meaning that there is an equal to sign. If this equal to sign is not there, it will be positive definite. Okay. And if the V of W of X is precisely greater than 0, which means it is positive definite, then the system is globally asymptotically stable. Okay, so there are two conditions here. As long as we have found that V of X such that V dot is less than equal to 0, that means that the equilibrium point is globally stable. But if V dot is less than 0, then it is globally asymptotically stable. You can think of it as a, what you call, if you were to look at a spring mass system, and I was looking at the total energy of the system, if there is no damper, then I would be having less than equal to 0. But if I had a damper, I'll precisely be less than 0. We'll try to take a look at an example, okay, so that this thing becomes a little clear. In fact, we do take a look at it right away. So let's say that we have our spring mass damper system, and we have its dynamics given by x dot is equal to v, and mv dot plus dv times v plus k of x is equal to 0. Okay. Assume here that the mass is positive, the stiffness is positive, and the damping value is also positive. For now, we are even assuming that the damping may not be just a linear coefficient, constant coefficient, but rather might depend itself on v. Okay. Here we are assuming that the damping itself will depend on the velocity v. Okay. In this case, we can choose V of X as the sum of potential and kinetic energy of the system, which is half mv squared plus half kx squared. Right? Everybody is familiar with this, right? The first term here is the kinetic energy, the next term here is the total potential energy stored in the spring. Now, if I take V dot of X, I see that V dot of X will be mv times V dot plus kx times x dot. Everybody with me so far? In the next line, what I'm doing is that x dot is nothing but v, right? So I'm taking v as common, and what will be left inside? M times v dot plus k times x. Yes? All right. And then, since I know my equations of motion is mv dot plus dv times v plus k of x is equal to 0. So the sum of these two terms will be equal to minus dv times v. Right? So therefore, since there is minus dv times v and there is a v which I am multiplying with it, it will become minus dv times v squared. Now, if we look at this function will always be less than equal to 0. Why? Because we assume that d is positive and v square will always be positive unless v is equal to 0. Everybody with me so far? Yes, no? Yes. Okay. All right. So then what's happening? The equilibrium point x comma v corresponding to 0 comma 0 is globally stable. We have shown that v of x is formulated as a function shown here, for which v dot of x will be less than equal to 0, and v of x is always greater than equal to 0. It is actually greater than 0 as long as I'm not at the equilibrium point. So all the conditions which we chose here are satisfied. Okay, and v of x is unbounded, which means as x and v go to infinity, v also tends to infinity, right? So under these conditions, I can say that the system is globally stable. Okay, but we will see that it's not just globally stable. We can say more about it here in this case, because we precisely know, because of the damping, the system will be asymptotically stable. But this does not give us that. This theorem which we have just now applied, it doesn't give us asymptotic stability, because x can be non-zero, but v being 0, the system will still have v dot equal to 0. Are you following me? If I was at any state x comma v, where x is non-zero but v is 0, so any state which looks like this, v dot will be equal to 0. So not just at the equilibrium point, but any point other than the equilibrium point. There are some points other than the equilibrium point at which v dot is equal to 0. So I can't say asymptotically stable. Okay, if it is going to be less than 0 at every point in the domain other than the equilibrium point, then I can call it asymptotically 0. Because definitely v dot being 0 implies that the system will slowly wind its way down to the 0 point. But here there seem to be some states where if I start, v dot is not 0. So then I have to wonder about whether it is globally stable. That much only I can tell. I can't prove asymptotically stability as of yet. Okay, we'll see how to do that in just a minute. Everybody with me so far? Is this part clear for everyone? Yes? Okay, so if it is clear, why don't we do one thing? Okay, so let's say I have a system x double dot plus x dot. Okay, let's call it 2x dot plus x minus x cube equal to 0. Okay, find me whether the system corresponding to, and let's say that I have, instead of x dot, I'll call this v dot. Okay, so find me the equilibrium point 0 comma 0. What can you tell me about it?
an appropriate potential function for this?
How do you choose the
Appropriate v of x for this potential function?
That's the question. That's why I wanted to confuse you guys. Okay? Think about how we would go about it. How to choose the v of x. Were we able to choose an appropriate Lyapunov function? Yes, anybody? Were we able to choose an appropriate Lyapunov function? What did we choose? Vallam, what can we choose as the Lyapunov function in this case? Or at least what did you think might be a possible option?
Like, I'm thinking it should have terms like whatever terms it will finally have, the v dot will should have like squares or something, and one's a common sign, so we can directly know whether it is going to be positive or negative.
So tell me the functional form you're thinking about.
I'm still looking at what it is.
Just based on the previous one, how would we go about it? Based on the previous example which we had, where we did not have this term, right? This second term, this term was not there. Correct? If that second term was not there, what did we choose?
Like we choose the half kx square plus half b square.
Correct. So it simply would have been x square by 2 plus b square by 2. Correct? If this cubic term was not there. But if the cubic term is there, it is causing a problem, isn't it? Why is it causing a problem?
Like after we write the v dot, we will not get like we get like minus 2v square plus x cube v, and then we can't determine exactly uh, whether it will always be positive or always be negative.
Correct. X cube v will not make any sense for us, right? Can we do anything to include, let's say, the potential energy due to that term as well? So suppose if I did something like this, minus x to the power 4 by 4, then what happens? Does it solve our problem? If I now take a derivative of v, what do I get?
Minus 2v square.
It will be x times x dot, v times v dot, minus x cube times x dot. Correct? But if I take v common, I'll get x minus x cube plus v dot, which becomes minus 2v square. Suddenly it looks like it is solving our problem. But is it really solving our problem?
Like it doesn't have x.
Does it have?
Yeah, it has the same problem as the previous one. Can't be asymptotically stable. Can only be globally stable, right?
Okay, that part is fine, but is v always greater than 0?
Oh, okay.
We didn't think of that, right? For very large values of x, what's going to happen? V will be actually negative. So this is not a good Lyapunov function. Okay, I gave you this problem in order to appreciate the difficulty in identifying a Lyapunov function. For not all systems, it is very easy to find out what the Lyapunov function might look like. Just notice that if I just change this sign from negative to plus, then things become easy. And then it is perfectly fine that you can prove global stability. Right? Whereas when it is negative, you can't prove global stability. And we know that it can't be globally stable because we saw that in the previous class. When we are looking at a system which has a stiffness x minus x cube, we have this eye-shaped region only inside which the thing is attracted by this origin. Anything outside, it doesn't get attracted to the origin but actually runs away. Something like that. So there is no global stability for the 0.00 in case of certain systems. Okay, the whole exercise this we were doing was to kind of get you in touch with how difficult it is usually to pick up a Lyapunov function. Sometimes if you're really having trouble picking up a Lyapunov function, you might really want to take a look back at the system and see whether at all it is even possible to have global stability in such a case. Sometimes it's not possible. In this particular example where x minus x cubed was there, the system is not, the equilibrium point 00 is not globally stable. It's only locally stable, isn't it? Is that making sense? Yes, no. It was more of a counter example to kind of make you think a little bit. Not quite sure whether that was having the desired effect. Yes, did it have the desired effect? You're able to appreciate now?
Yes, sir.
Yes. Okay. All right. So that's the idea. The moment when I put x plus x square, then what happened? You see, when I had x minus x square, there were three equilibrium points. One at minus 1, 0, 1, 0, and 0, 0. Correct? But when I introduced x plus x cube, how many equilibrium points does the system have now? Okay, go ahead, find out the equilibrium points for this system.
So the origin here will be stable. It will be like an equilibrium point.
It will be the only equilibrium point.
Yes.
Right? The origin is the only equilibrium point in this particular case.
Yes.
Everybody seeing that?
Yes,
Yes,
only
sir.
0, 0.
Only 0, 0.
Only 0, 0. There are no other real equilibrium points.
Yeah,
You may have
should
imaginary points.
Should be
but
imaginary. Yeah.
that doesn't help us. Right? So for a real part, there's only one equilibrium point, which is this case. And in this case, choosing a Lyapunov function like this, you can actually show that it is globally stable. Okay, so that's what I'm trying to get at. These methods, you have to take them with a pinch of salt. The value of V, which I need to choose, is something which does seem to be a problematic thing, right? Later on, you will see that there are certain methods to choose V so that we can appropriately tailor it. In fact, you will see later on when we look at backstepping controller that we actually use this idea of formulating a V in such a way using the control law that our system is rendered to be globally stable. We try to utilize this idea there. Okay, we try to tweak the value of V slowly over steps iteratively until we get to a point where we can now act as a point where the equilibrium point that we want to track is globally stable. Okay, more on that later. Yeah, those are some of the concepts which I have not covered yet. So we'll look at them as we get closer to that point. Okay, hopefully for now it is clear that when I want to apply, how do I apply this Lyapunov stability criteria is more or less now making sense. Okay, all right. So we saw in this case that the equilibrium point 0, 0 is globally stable for this case of a linear spring mass system, spring mass damper system. However, in many cases, we can also prove globally asymptotically stable systems using what is called a Krasovskii-LaSalle's theorem. Okay, and this is kind of looking at a specialized set of criteria. Okay, specifically, we are looking for systems where V dot is negative semi-definite. Okay, just like where we saw here, it is negative semi-definite. In which cases there are certain cases where even though we do not get global asymptotic stability from the Lyapunov's direct method, there may be something else which we can do in order to prove global asymptotic stability. That is what we'll look at now. So this Krasovskii-LaSalle's theorem again continues back on the same process, that we have a V which is continuously differentiable such that V tends to infinity as mod of x, the norm of x goes to infinity, and V dot of x is less than equal to 0, which means it is negative semi-definite for all x. Then we try to identify omega. Okay, let's say omega is the set of all the points where V dot is equal to 0. Okay, we saw that V dot is negative semi-definite over the entire regime. We want to identify those points where V dot is exactly equal to 0. Okay, once we have this set omega where V dot is equal to 0, we want to find the M, which is the largest invariant set in omega. What do I mean by this invariant set? In the sense that if I begin at that set, I continue to be in that set. That is what it means as an invariant, which means if I start at a point and I continue to be at that point, it would be an invariant point. That is what is the equilibrium point, right? We define equilibrium point as a point where we start and we continue to be there. So if this set of points omega, we has a largest invariant set to be M, then we can show that all the solution sets of T will actually converge to M. And if M is only composed of that equilibrium point alone, then we can say that that point is globally asymptotically stable. Let's take a look at an example to understand this. It may not be so straightforward to figure out from the text of the theorem. So if we go back to our spring mass damper system, we saw that V dot is actually less than equal to 0. Now, if we wanted to identify where is this V dot exactly equal to 0, we see that omega here is the set of all values where x belongs to the real numbers and v is equal to 0. For all of this set, for all of these points, v dot will be exactly equal to 0. Everybody with me? Now, of these points, I want to see which are the invariant points, which means that if I begin at those points, I continue to be in set omega. Okay. If I start at the origin point, v equal to 0, x equal to 0, I know that I'll continue to be there because it's an equilibrium point, right? But if I start at v equal to 0, but x not equal to 0, say let us say x is positive, okay, then what is happening? Wherever v is equal to 0, we know that mv dot will be equal to minus kx. Because v is 0, we know that our equation is mx double dot or v dot plus v of v times v plus k of x is equal to 0. This term is anyway going to be 0 because v is 0. Correct? So what will be left is mv dot is equal to kx minus kx. Which means if I start at any non-zero x, what is happening? V dot is not equal to 0. Right? Which means I'm moving away from that set because V dot is not equal to 0. If I start at that point, over time V will no longer be 0. Is that making sense?
Sir, can you tell it again?
Yeah. See, if I'm starting at a point where V dot is not equal to 0 and x is not equal to 0, if V dot, this is small v dot, okay, velocity, derivative of that velocity or acceleration is non-zero, means that at the next time instant v will no longer be 0. If the body has some acceleration and its current velocity is 0, at the next time step I should see the velocity change, right? Which means it will no longer be in that omega set anymore. The point will no longer be a part of omega set anymore because omega set was all the points where v was equal to 0. Everybody following me?
Yes, sir.
That time the body have only the displacement and accelerations only.
Correct. It only has a displacement and an acceleration but does not have a velocity. The velocity is 0. Okay. You can think of it as a spring mass damping system, or if suppose you are on a swing, at the highest point on the swing, your velocity is 0, but the acceleration is not 0, nor is the displacement 0. Making sense? So therefore, that point cannot be an equilibrium point. You reach there instantaneously and then you come back again. You can't stay there. If I'm on a swing and I'm trying to swing along, I can't stay at that pinnacle point. That's what it means. Everybody with me so far?
Yes, sir.
Yes? Okay. Krishnavelu? There, right? If I'm swinging like this, I'm going back and forth. Okay? I'm going back and forth. I can't stay at this point, even if I wanted to. I can momentarily be there, but I can't hold on to be there. There's no way for me to just stop and be there. Right? So it's not an equilibrium point. Eventually, over time, I will start coming down because my velocity will now start increasing. So I'll no longer be, it's not an invariant set that I can't start there and continue to be there. Okay? So the system will move away from v equal to 0 except when we are at the equilibrium point. Okay? Except at that point, no matter where else I start in that omega set, I will move away from the omega set over time, which means that the only invariant, largest invariant set which the system cannot leave of omega is just the equilibrium point 0, 0. And Lassalle's theorem basically tells us that if that is the only point which is invariant in the entire omega set, which corresponds to v dot equal to 0, okay, where the derivative of the Lyapunov function is equal to 0, then the system will be reaching that point asymptotically, which means that point will be now asymptotically stable, globally asymptotically stable. Is everybody with me so far?
Yes, sir.
All right. Okay, so then this point is asymptotically stable. All right. Now let's discuss about the idea of global exponential stability. Okay, let's again consider the same system, x naught equal to f of x of 0 equal to x naught. We are looking at an equilibrium point, xe equal to 0, and again we have this function v as a continuously differentiable and radially unbounded function. But in addition to the previous conditions, we are able to show that v of x is equal to some x transpose px. So P here is a matrix, okay, and x transpose Px is always greater than 0, and V dot is given by minus x transpose Qx, where Q is also a matrix, and this is always less than 0 for all x not equal to 0. And we have these constant matrices P and Q, which are positive definite. Then x of E is globally exponentially stable. Okay, so as long as I can find matrix, the V can be expressed as x transpose P times x, where P is some matrix which is positive definite. Okay, and similarly I have V dot as minus x transpose Q times x, where Q is some positive definite matrix. If I can show that V and V dot follow the procedures where I can find these or identify these matrices P and Q, which are positive definite, then I can say that the system is actually globally exponentially stable. Okay, which means that it is a stronger condition than asymptotic stability. It is saying that actually there is a bound on how quickly the system will die back down to 0. Okay, and that bound can be expressed in terms of the eigenvalues of P and Q matrices. Okay, does everybody understand here when I say a matrix is positive definite, what do I mean by that? What do I mean by that?
For all x not equal to 0, like x transpose times that matrix times x will be greater than 0.
Greater than 0. But how do you prove that a matrix is positive definite?
Forgot.
You look at basically the eigenvalues of that matrix.
Yeah, it should be less than
Okay, and if you look at the eigenvalues of that matrix, then you'll see that all the eigenvalues are positive, means that it is positive definite. Okay, just trying to make sure that yeah, the matrix is positive if all its eigenvalues are positive. Okay. Positive semi-definite means some of the eigenvalues can be 0. Negative definite means all of the eigenvalues are negative. Okay. So on and so forth. So the idea here is that as long as I can prove that the P and Q are positive definite matrices, I can actually find a bound on the convergence. And this alpha, the rate of decay of those solutions, will be bounded by the minimum value of the minimum eigenvalue of Q divided by 2 times the maximum eigenvalue of P. That will be the bound rate. So it will be faster than that. It will decay to 0 faster than that. It will decay to the equilibrium point faster than that. It is a much stronger condition than what we specified for asymptotic stability. In asymptotic stability, we do not have a bound on the convergence. But in an exponential stability, we have a bound on the convergence. Okay, now when it comes to so far what we have discussed, we have looked at the autonomous systems. But many cases, we are actually going to be dealing with non-autonomous systems, which means that our differential equation on the right hand side will have some explicit terms which are depending on time, which may be something like weather causing a wind forces, wave forces, or current forces, which will be time varying. So we need to look at non-autonomous systems at some point down the line. Okay. Although in some cases we can get away with the idea of autonomous systems, but in general, most of the systems which we are interested in practically will be non-autonomous in nature. So it is important to look at what is going on with these non-autonomous systems. The idea here is that when we look at these non-autonomous systems, we also have to deal with this explicit dependence in time. Okay, so we have to look at a uniform convergence rather than a point-wise convergence in terms of mathematical sense, which means that the convergence must happen at all times at once. It should not be at a point-wise, time-wise. At a particular time, the system is stable, but at another particular time, it is unstable. We can't deal with that in some sense. And I'm not being rigorous here, okay? The mathematical rigorosity is not there when I'm talking about these things. I'm talking about an intuitive sense here. Okay. All right. So in that case, also we can prove the stability using Lyapunov theory. So before we do that, there are a couple of things which we need to get into place. So let's look at that. So the first theorem which we will be looking at is called the Barbalet's lemma. And this has something to do with the fact that if I have a function phi, which is a scalar function mapping from positive real values to some real value, be a uniformly continuous function, and suppose that limit t tends to infinity, integral 0 to t phi of tau d tau exists and is finite, then we can show that the limit t tends to infinity phi of t will be 0. Okay, what it is telling, it is basically saying that the area under the curve, if I plot the value of phi versus time, okay, so let's see if so let's say I start and do something. So the area under this curve exists and is finite. That is this integral. Okay, it exists and is finite. Then I can actually show that as time tends to infinity, this thing has to go down to 0. If it does not go down to 0, it is very intuitive to understand that you probably will not see it converge to a finite value. Even if in the what you call the simplest counterexample can be, let's say I have a constant value. Okay, but it extends all the way into time t equal to infinity. I know that the area will not be finite. right? The area will be infinite in this case. Is that making sense? Yes. So
Yes.
that's what it's basically saying, that if I have any function that is uniformly continuous, and suppose that limit t tends to infinity, integral of this thing exists and is finite, then this must tend to 0. It means it guarantees a global convergence. Okay. Bar-Pillet's lemma is particularly useful if there exists an uniformly continuous v that we were looking at, the Lyapunov function. Notice that now its characteristic has changed. So instead of having that Lyapunov function be a mapping from n cross 1 vector to a real value, it now is an n cross 1 vector comma time, right? V is a function of x comma t instead of now. Instead of previously it simply being v of x, right? So therefore this function, if it satisfies v is greater than equal to 0 and v dot is less than equal to 0, and v dot is uniformly continuous, okay, then according to Bar-Pillet's lemma, we have that limit t tends to infinity, v dot will be equal to 0. Okay, what I am essentially saying is that, okay, so if I go back to the Bar-Pillet's lemma, my phi is here v dot. Okay, I'm saying that if I take my value of time limit t tends to infinity, so if t is v of t minus, then integral phi d tau 0 to t is nothing but v of t comma x. If phi is v dot, then integral of phi will be v, right? So as long as v of t comma x exists and is finite, because we do know that this Lyapunov function must exist over our entire domain, some value it must have, right? As long as it exists, I can show that using Bar-Pillet's lemma that limit t tends to infinity, v dot will go to 0. Okay. This requirement that v dot should be uniformly continuous, which is the fact that I have taken here, okay, can be checked by using that v double dot is bounded. Generally, when I construct my v, I can always verify that if I take a second derivative of v, whether it is bounded or not. This uniformity is something which we have to worry about whenever there is a time dependence. Because whenever there is a time dependence, I can't prove it for one instant and say that it will work fine. There has to be uniform convergence across all times. That's what it is saying. Okay. The strongness of the condition with variation with time, when I need to account for, I need to make sure that I'm not just looking at globally asymptotically stable, but I should now talk about uniformly globally asymptotically stable. It should be uniformly be applicable across all times. That's what it means, okay? Intuitively. Now we're really not going into the mathematical rigor here. We don't require it also for our course, but if you're doing a course on nonlinear dynamics, you will then learn about it and then further. Okay. Now let's look at how do we apply the Lyapunov's methods for the non-autonomous systems. And you'll see that this is kind of looking like our Lyapunov's direct method, but extended to the non-autonomous systems. So again, we have a system x dot is equal to f of x comma t, starting from an initial condition x naught equal to x of 0 equal to x naught. And I'm looking at the conditions for this equilibrium condition to be stable or not. Again, I'm able to formulate a function v of which is a function depending on x comma t, and let's say v of x comma t is greater than 0, which is positive definite, and v of 0 is 0, okay, and v dot of x comma t will be del v by del t plus del v by del x times f of x. Notice that here there are two variables that the function depends on, so we have to apply the so-called chain rule. of differentiation. Okay, so that is what is leading us to this first term, del v by del t plus del v by del x times dx by dt. And this dx by dt is x dot, that is equal to f of t comma x, and that's why you get this term right here. If v dot is less than or equal to 0 and v of t comma x is tending to infinity as x goes to infinity, which means it's a radially unbounded function, we are able to formulate a v under these conditions, okay, then the x of t are uniformly globally bounded, okay, in addition, and the limit t tends to infinity, w of x of t tends to 0, okay, which means that w is nothing but this bounding function here. Okay, so the idea still remains the same. If w of x is greater than 0, which is positive definite, then the equilibrium will be uniformly globally asymptotically stable. If the w of x is greater than or equal to 0, it is uniformly globally stable. That's all. The only difference it has added is the variation with time, causing you to talk about uniform stability. So instead of previously we calling it globally asymptotically stable, we now call it uniformly globally asymptotically stable, meaning that it will occur or it will work at every time instant that I want to choose. Is that making sense?
Sir,
Yes.
so what is the significance of W of x, sir?
The W is here basically to say that suppose this, what do you call it? It's basically to specify whether this inequality is greater than, less than 0 or equal to 0. That's what I want to specify in a clear terms. That's what I'm saying here. I'm just calling it a name. Instead of writing this entire expression, I'm just saying that if all of this is bounded by some W of x, and that W could be simply be 0 for all I care, across all x, okay? In which case the equality directly holds, isn't it? But the point is, as long as it is bounded and less than or equal to 0, v dot is bounded and is less than or equal to 0, then the system is globally stable. If it is strictly less than 0, okay,
Asymptotically.
then it is asymptotically stable. Okay, it's a question of a notation why I want to get this part here, because I'm calling v dot is less than or equal to minus w of x, and if w of x is greater than 0, then I know that the system will be asymptotically stable. If it is greater than or equal to 0, then it will be just globally stable. That's all. Just a question of convention. It really doesn't have any particular meaning to it.
Sir, but if W of x is less than 0, that inequality won't hold, right? Like,
Yeah, w of x has to be greater than 0. That's right. If w of x is greater than 0, only then positive definite, only then the system is globally asymptotically stable. But we are basically looking at this v dot to be less than 0. That's what we want to look at. Okay, so rather than worrying about the where the w is coming from, you just remember it in terms of what is happening to v dot. As long as v dot is less than 0, we know that the system is stable. If it's strictly less than 0 overall the entire domain, then it is asymptotically stable. Otherwise, it is simply globally stable. That's all.
yes, sir.
When we are looking at non-autonomous systems, make sure that you understand the idea that it's uniformly globally stable or uniformly globally asymptotically stable. That's the only difference. Okay, all right. So this next portion, which is the uniform semi-globally exponentially stable of proportional LOS guidance schemes, we'll cover this a little later. Okay, we are going to cover this when we talk about the LOS guidance schemes. Let us first discuss about that and then come back and discuss about its stability. Okay, at that time I'll cover this. So in essence, we have covered the main ideas of stability today with respect to autonomous systems and non-autonomous systems. Okay, and always we have to deal with a Lyapunov function that we formulate, and we want to check that the Lyapunov function is greater than equal to 0 over the entire domain, and v dot is less than equal to 0 over the entire domain, with equal to 0 being only at the equilibrium point. Then we can say that the system is globally stable. Okay, if specifically v dot is strictly less than 0 over the entire domain, then you know that it is globally asymptotically stable. And we looked at the ideas that you can think of the Lyapunov function as an energy function of sorts. Okay, but the main idea here is that you don't have to choose it to be the energy function. You can choose it to be whatever you want. And that was the great idea behind the Lyapunov's method. It was not restrictive in the sense that you only have to choose energy and then demonstrate these effects, but rather choose any function of your liking as long as it follows these certain criteria and you show that it is following the certain properties of V which it should follow, then you can prove the stability of the system. Okay? And these methods are very powerful. You will see that when we are looking at our guidance schemes and control schemes, when we want to prove robustness, which means that when I have a additional disturbance acting on my system, whether my controller will be able to reject those disturbances and still give optimal performance. These sort of methods come in very handy to prove mathematically that yes, they are robust in nature. Okay, so particularly for robustness, the exponential stability is particularly important. We'll take a look at them as we start discussing the difference guidance laws and nonlinear guidance laws and nonlinear controls. Okay, so next class we'll go back to our guidance scheme and we'll start discussing about the line of sight, proportional guidance, and vector guidance fields. All right, so let me stop right here. Are there any questions before I stop recording? Questions? Okay, so let me stop recording here.